Drawing ray diagrams for converging lenses. Number 1. The object is placed more than twice the focal length from a lens. Let us consider the following question. Describe the image formed by a converging lens, with a focal length of 6 cm, when the object is placed 14 cm from the lens. We will need to draw a ray diagram in order to fully describe the image in terms of location, orientation, whether it is real or virtual, as well as its magnification. To proceed, we first take a piece of graph paper and draw a horizontal line, cutting the paper in two. We label this horizontal line the principal axis. Now draw in the location of the lens. It is always a good idea to place the lens approximately at the center of the graph paper. Draw a vertical line at this position, with up and down arrows, in order to represent the location of the lens, and label it optical axis. The lens is a converging, or convex lens, so we draw it as an up and down arrow. Some people draw it as a large converging lens, others draw a small converging lens. It makes no difference, the position of the lens is only a representation, to allow us to draw the construction rays correctly. Note the location of the focal length compared to how far away the object is. This means the object will be just over twice the focal length away. From the original question, the object is 14 cm to the left of the lens. This means we can use a scale of 1 cm on the graph paper to equal 1 cm in distance. Now mark on the position of the principal focal points on either side of the lens. In this case 6 cm from the optical axis. Mark each principal focal point with a capital F. Mark on the position of the object. The object is represented by a vertical arrow. It does not matter how high the arrow is, it has no effect on the overall outcomes. An object 4 cm high is usually sufficient. Label it object. Now check that the principal axis, optical axis, principal focal points and object have all been clearly labeled. It is also good practice to mark in the focal length distances from the optical axis. Now we will draw 3 construction rays. The rays are drawn in order starting out horizontal, and turning clockwise. Start the first ray from the top of the object. Draw a horizontal line until it reaches the optical axis. Then draw a line from that end point, passing through the focal point on the other side of the lens, and continue the ray to the end of the graph paper. The second ray goes from the top of the object and is a diagonal line that goes straight through the optical center and continues on until the end of the graph paper. For the third ray, draw a line from the top of the object through the nearest focal point, and continue until it reaches the optical axis. Then continue this ray as a horizontal line to the right of the lens. All 3 lines should meet at a single point. This is where the image is in focus. Draw the image as an arrow and label it image. From the diagram, we can now find the image distance, by measuring the distance from the optical axis to the image. In this case it is 10.4 cm. The image itself is upside down compared to the object. The image is said to be inverted. The image is on the opposite side of the lens to the object, so the image can be projected onto a screen. The image is, therefore, real. The image is smaller than the object. It is said to be diminished. We can calculate the magnification, which is image height divided by object height. This gives a magnification of 3 divided by 4, or 0.75. At A level, these approximate answers can be verified by use of the lens equation. By using 1 over u plus 1 over v, equals 1 over f. Or 1 over v equals 1 over f minus 1 over u. Substituting in the values, all in centimeters, gives 1 over 6, minus 1 over 14. This gives 1 over v equals 0.0952. Or v equals 10.5 centimeters, hence the image is 10.5 centimeters from the lens and is a real image. The magnification is given by m equals u over v. Substituting in the values gives m equals 10.5 divided by 14. This gives a magnification of 0.75. The image is diminished. The approximate graphical method, therefore, gives results consistent with this more rigorous approach.